All right, so we're going to look at something a little bit more fresh today. This is going to be equations and graphs of polynomials. So basically, the name of the game today is we're going to be looking at how the equation of a polynomial, especially when it's in fully factored form, can correlate with what its graph looks like. We've kind of touched on some elements of this already, but we're going to get a little bit more practice at basically looking at how graphs and equations are related. Anyway, here we go. So we do have a busy day ahead of us. I don't know how long this will be, but I do expect it'll be on the longer side of things. In the last few days, we've slowly built on the idea of factoring a polynomial. So just to kind of refresh your memory, how can we find the values of x that make y equal to 0? You might remember I told you there was a really nice shortcut of using your graphing calculator to kind of cheese this a little bit, but there's other ways you can do it without using your graphing calculator, of course. But the better question is, where do we go from there? How do we actually start breaking it down and finding all the factors of a polynomial? Well, regardless of this, today we're going to look at how to determine how many times a single factor appears in factored form. So in other words, sometimes you might have, for example, x plus 2 being a binomial factor, and it might actually appear more than once. We want to be able to determine how many times factors appear in factored form. We're going to call this multiplicity. It'll make more sense when we look at that later. Lastly, of course, we'll learn how to sketch rough graphs from an equation. So in other words, if I gave you an equation of a polynomial, we're going to actually start talking about how we can make a really rough sketch about what that equation might end up looking like. Anyway, let's get going. So just a brief investigation first. The graph of the fully factored polynomial function p of x equals x plus 1 times x minus 3 squared is shown. What do you notice about the factored function, so this form right here, and its graph? Is there anything you see to connect them? Well, one thing hopefully you see is, you might remember from previous days, we've talked about how these binomial factors are actually just ways of finding your x-intercepts. So for instance, this one would be an x-intercept of x is -1. That would represent that guy right there. And this one would be x is positive 3, which would represent this guy right here. But what I want you to notice is one of these factors being x minus 3 squared. How does this get represented on the graph? Think about what that x-intercept really looks like at x is equal to 3. If you kind of notice, you might notice that just around x is equal to 3, like just locally here, it almost looks like a mini quadratic, just within that one little region. That's actually not a coincidence. When you have a 0, or in other words, an x-intercept, or in this case, in factored form, just a binomial factor, the x-intercept itself is going to kind of take the appearance of what that factor looks like. So just in the neighborhood of x minus 3 squared, or rather of x equals 3, it's going to look kind of like an x minus 3 squared kind of function. It's going to look like a quadratic right there. That's not actually just limited to factors that are squared. If you had a cubed function, it'll look like a cubic right at that point. This one right here, x is -1, you might notice it kind of looks like a straight line, more or less, at that point. And that's kind of like a linear equation. So bottom line, what I'm trying to get at here is when you have a polynomial factored in its binomial factored form, your x-intercepts are going to look very much like what their factored form looks like, especially if you have more than one, like this x minus 3 squared. That would be 2 x minus 3s that you would have in there. Anyway, moving on. So this is a concept called multiplicity. The multiplicity of a 0, also known as an x-intercept, represents the number of times a factor is repeated in the function. So in other words, if you fully factor a function, you have something like x minus 2 showing up more than once, then it has a multiplicity greater than 1. So in the last example, the 0 x is equal to -1 has a multiplicity of 1. And that's because it only showed up one time right here. The 0 x is equal to 3 has a multiplicity of 2. And that's because it shows up twice. Or in other words, we had x minus 3 squared. The sum of the multiplicities of all the zeros of a polynomial will equal the degree of the polynomial. This point is huge. That is super, super important. You might notice on that last example, sorry to jump back again here, but you might notice that if this has a multiplicity of 1 and this has a multiplicity of 2, the sum of that is a multiplicity of 3, which makes this whole thing a cubic function. The degree of the entire thing is equal to the sum of the multiplicities of each 0. Now, the shape of the graph nearby that 0 will look like a miniature version of the polynomial with a degree of the multiplicity of that 0. So kind of like what I was saying on the last one, because we had that one 0 where it was x is equal to 3, the binomial itself looked like x minus 3. Because that was squared, just around that region, it looked like a little miniature x squared function, just kind of for your own interest there. Anyway, so here's an example. Suppose we have the polynomial f of x equals x minus 1 times x plus 2 times x minus 1. What are the multiplicities of each 0? Well, just remember, 0 is another word for an x-intercept. So we have an x-intercept of x equals 1. That would be for this one and this one. And because that shows up twice, we can say that this has a multiplicity of 2 because it shows up twice. The other 0 we have is this x plus 2, which means x would equal negative 2. That would be our other 0, our other x-intercept. That one has a multiplicity of 1. So the multiplicities of each 0 here is x is equal to 1 has a multiplicity of 2, and x is negative 2 has a multiplicity of 1. If you notice, the sum of all the multiplicities here, 2 plus 1, gives us a total sum of 3. If you were to expand this whole thing out, it'd be a whole bunch of multiplying here, but if you were to expand this whole thing out, you would find you'd have an x cubed function, or in other words, a cubic function. Anyway, moving on. So tangents and points of inflection, this is kind of reiterating what we were already seeing with what the shape of the graph looks like around this. If you have a 0 that has a multiplicity of 1, it's going to pass straight through the x-axis. So in other words, wherever that x-intercept happens, it's just going to basically be a straight line through it, more or less. So basically, it's just a mini linear equation right nearby the x-axis. And that's because it has a multiplicity of 1, which is like a degree of 1, which is a linear equation. A 0 that has an even number multiplicity, so 2, 4, 6, etc., will be tangent to the x-axis. Tangent is just kind of a funny word that means it grazes but doesn't pass through. Oh yeah, I even had it right there. So this means it will just graze the surface of the x-axis but not cross it. I wasn't actually even reading that. I was just kind of thinking to my mind there. Anyway, last one here, a 0 that has an odd number multiplicity greater than 2, so a multiplicity of 3 or 5 or 7, will be a point of inflection on the x-axis. I really don't like that description. It just kind of does like a weird, like little cubic kind of looking thing. And that doesn't matter if it's a degree of 3 or a multiplicity of 3 rather, or a multiplicity of 5, etc. But it'll do this weird point of inflection thing. That's not to be confused with one that's going to pass more or less straight through. This sometimes can look like a bit of a point of inflection. It might kind of look like that. That doesn't mean it's a multiplicity greater than like 3 or 5 or 7, but it is just something you'll have to watch. Anyway, we'll get some actual look at this here. First of all, what types of multiplicities do you see in this one? Well, this is the exact same graph we had before, so you can probably tell that this is going to be a multiplicity of 1 because it passes straight through, and this one has a multiplicity of 2 because it forms like a little mini quadratic. This one is a little sneakier. This one certainly has a multiplicity of 1. This one also has a multiplicity of 1. This one in the middle, though, it almost looks like we have a change in concavity because it goes from like concave down to concave up. But in all truth, it looks like it's a pretty straight line right there. So I would call that a multiplicity of 1 as well. And as a matter of fact, when you see the function itself, you can see it's a cubic function, which means the sum of all the multiplicities has to equal 3. So I know that that one's 1 as well. So in terms of increasing multiplicities of even functions, from left to right, this graph that we've got here shows f of x is x plus 4 squared, hence why we have x is negative 4 as a 0. This next one is g of x is x minus 1 to the power of 4. That's that blue function right here. And then the last one over here is x minus 6 to the power of 6. Notice that there's a little bit of a difference in the shape of the graphs here, and it's hard to kind of explain what this looks like. But if I were to ask you, what do you notice about the shape of the graph as the multiplicity increases? Something really weird happens right at the 0. This red graph here, which is x plus 4 squared, it's just a pretty nice looking quadratic right there, right? It just kind of does that normal little quadratic shape. It's tangent to the x-axis. It just grazes the surface right there. It is what it is. When we increase the multiplicity, though, from 2 to 4, that's what this blue one is. Look at the shape of it down here. It kind of looks like a quadratic that someone sat on. And that's actually pretty much about as good of an explanation as I can give. The higher multiplicity you have for even functions, basically the more squished it looks. And that comes even more true for this x minus 6 to the power of 6. That is a multiplicity of 6. And look how like squished it looks. It almost looks like a rectangle down there. But that's basically what happens as we increase the multiplicity. So keep an eye out for that. If you ever saw something like this, you probably don't have a multiplicity of 2. You probably have a multiplicity of 4 or 6 or something even higher than that. For odd functions, something else happens here. From left to right, we see x plus 4 cubed. So notice that's a pretty clear cubic graph. It's not passing straight through. That is certainly an odd multiplicity there. So a multiplicity of 3, of course. This next one is x minus 1 to the power of 5. And this last one is x minus 6 to the power of 7. This one is a little bit more subtle. But what do you notice about the shape of the graph as the multiplicity increases this time? Well, what I would say, again, it's really hard to tell. For the one that's a cubic function, it's just a pretty straightforward, normal kind of cubic function. But for these other ones, it looks like it's kind of stretched along where the actual x-intercept is. And the higher your degree, the more stretched it's looking. So basically, it's like it's taking its time to cross the x-axis when you have a higher degree like that. Again, it's pretty subtle. At face value, you might not even be able to notice the difference, and that's okay. But I want you to kind of think about what these different multiplicities might end up looking like. All right, so this one is a lot more important. I actually really appreciate this question because it's really going to get us thinking. As a matter of fact, I would appreciate if you gave this one a try, but I'll read it first. Megan sketched the following graphs into her notes. So she drew these rough sketches of 4 different graphs. For the first part of this, I want you to label on the graphs, the possible multiplicities of each 0. So just take a stab at each one of these. It doesn't matter if you guess it wrong, but just take a stab. What do you think the multiplicities of each 0 are? Pause the video here and give it a try. All right, so I'm going to go over this one now. I'll actually label it right on these. I'll start with the first graph here. This 0, in other words, this x-intercept, that kind of looks like it has a multiplicity of 2. You could argue that. You could say, oh, maybe it's a multiplicity of 4. But I don't see the real like sat on dip in there. You know what I mean? But if you see that, sure, you could say it's a multiplicity of 4. That's fine as well, right? But I personally would go a multiplicity of 2 there. It certainly isn't an odd multiplicity, like it's not 1 or 3 or 5 because it doesn't pass through. But 2 would be reasonable. This next one over here, this one definitely looks like a multiplicity of 3 to me. It's not a multiplicity of 1 because it doesn't just go straight through. It does that weird little like curve kind of divot there. So that probably is a multiplicity of 3. I wouldn't go so crazy to say 5 or 7, but 3 is probably accurate enough. On the second graph, this multiplicity right here is super clear. That's a multiplicity of 1, perfectly straight through. Like that's crystal clear. This one looks like it has a multiplicity of 2, and then this one has a multiplicity of 1 because it's also going straight through. This one down here looks like we have a multiplicity of 1 at this x-intercept, another multiplicity of 1 at this x-intercept, and then this one, that looks like a multiplicity of 3 right there, because notice it does that little cubic divot right there. As for this last one, I would say this is a multiplicity of 2. The next one is a multiplicity of 2. And then lastly, notice it goes straight through right here, just barely on our x-axis there. I would say that's a multiplicity of 1. All right, question B says, which graph could represent a 4th degree polynomial? Pause the video here and see if you can figure that one out. Okay, so the trick behind this one is, hopefully you remember from earlier in the lesson, the sum of your multiplicities equals the degree of the whole polynomial. Well, assuming I've done this correctly, this first one would probably have a degree of 5 because 2 plus 3 is 5. This next one is 1 plus 2 plus 1. There it is right there. That's our degree of 4. So I'm going to say it's the second one. But just for fun, I'll continue going on these other ones here. 1 plus 1 plus 3, that looks like it's a degree of 5. And 2 plus 2 plus 1, that would also be a degree of 5. So kind of interesting there, the degree of 5 on a whole bunch of these, but the second one is definitely a degree of 4. You may also remember from way, way earlier in this unit, we did talk about looking at what the shape of different kinds of polynomial graphs are. Even functions like 2, 4, 6, etc., they will end on the same side of the x-axis. So notice this one ends down in quadrant 3 and quadrant 4, so both below the x-axis. That tells you right there that has to be an even function. Odd ones will end in opposite sides. So all of these end in opposite sides, so clearly they're all odd functions. Question C, in which of the graphs is the leading coefficient positive? Now, that actually alludes to what I was just talking about. It's been a long time since we've talked about that. A positive leading coefficient, the easiest way to remember this is it'll end in quadrant 1. So I can tell you right now, graph 3, there we go, graph 3 definitely has a positive leading coefficient because it ends in quadrant 1. Notice also graph 4, so I'll say this and 4. Graph 4 also ends in quadrant 1, so it is also a positive leading coefficient. That's the easiest way of going about it, to be honest. You really only have to look at quadrant 1 to tell what the leading coefficient is, whether it's positive or negative. If it doesn't end in quadrant 1, then you know it's a negative leading coefficient, just like these other ones do, right? Moving on. All right, so here's some fun. Consider the polynomial function that, quite a big one, right? Graph the polynomial in your graphing calculator and then roughly sketch what you see on the provided grid. Use this window. So remember, these window settings means this is your min, this is your max, and this is your scale. And same with this, min, max, scale. Pause the video here, give this one a try. I will go over it in just 1 second. All right, so hopefully that was enough time for you. First of all, I would draw your scale on this one. So we're using this scale in your graphing calculator. So I'll kind of try to match this on my grid that was provided. Do my best to get these axes down. So this is my y-axis. My x-axis is not perfectly in the middle. It's kind of down a little bit, so I'll put it about right there. That's looking okay, not too bad. Awesome. In terms of putting my scale on here, let me just count on my graphing calculator. It goes up 1, 2, 3, 4, 5, 6, 7. I wonder if I can skip count by 2. 1, 2, 3, 4, 5, 6, 7. Yes, I can. So I'm going to go here, 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 and here. So this would be in our Y scale. Just notice that's representing we're going up by 20 each time. So 20, 40, 60, 80, 100, 120, 140. I think that was actually perfect. I drew that line exactly where I needed to. Going down this way, that would be negative 20, negative 40, and negative 60. And then in terms of my X direction, remember, we're only going from negative 5 to 5. So once again, I'll skip count by 2. I'll say this is negative 1, 2, 3, 4, 5, and then 1, 2, 3, 4, and 5. So I'll just label that. I know how much of a pain this is to label a graph like this, but it is really important. I've seen in the past some students just don't label their graphs, and that's not really any use to anyone, because it doesn't really do us any good if you don't have a scale put on your graph. Anyway, now for the fun part. Now we're actually going to roughly sketch this graph. The key word there is rough. In all honesty, just as long as you get some of the key points in there sort of where they need to be, that's all we really care. What I notice on my graphing calculator is that we clearly have 2 zeros. One of the zeros we have is here at negative 3, and another 0 we have is over here at positive 2. Now, the one at negative 3 looks like it's probably a multiplicity of 2 because it has kind of a quadratic look to it. But before I draw it, I also want to acknowledge that we have a y-intercept that looks like it's somewhere between 60 and 80. So I'll put a dot right there just to help guide my graph. And it also looks like we have a bit of a maximum at about negative 1 and then close to 100. Not quite 100, but pretty close. Anyway, so I'm going to sketch this now. Again, roughly sketch. I'm pretty forgiving when it comes to this, but we're going to kind of draw like a quadratic looking thing right here. That's going to come up. Oh, that was terrible. That was too much of a V point. Let me try that again. Quadratic looking thing. There we go. That's better. Coming up this way, it's going to reach a max, and then it's going to kind of swivel down this way. And then as it swivels down, it becomes like a cubic intercept right here. So it kind of goes, and then it kind of goes down like this. Again, very key word there is rough. Like this is looking pretty miserable as far as I'm concerned, but you get the general idea. We don't have to be perfect artists at this. I certainly am not. But as long as you get the right general idea down, that's really where we're going with this. All right, so question B, this is what's a lot more important than doing a really stupid rough sketch of a graph. Complete this table. For description, I just want you to state whether it passes straight through the x-axis, if it's tangent, or if it's a point of inflection. So just judging by the graph we had before, like I'd rather look at the one on my calculator, but here's a graph we had before. Clearly we have 2 zeros. One of the zeros is at x is negative 3, and the other 0 we have is at x is equal to positive 2. And this was crystal clear because of our really solid scale that we had on our graphing calculator. Now, the multiplicity of x is negative 3. That one clearly has a multiplicity of 2. So I'll go into this chart here. I'll say this one has a multiplicity of 2. And then as for x is equal to 2, there we go. As for x is equal to 2, that one looks like it has a multiplicity of 3 because it doesn't go straight through. It does that cubic kind of thing to it, right? So I'll say this has a multiplicity of 3. Now, if I'm going to describe these using these phrases here, A multiplicity of 2 is certainly tangent to the x-axis. That just means it doesn't pass straight through. It just kind of grazes the surface. And then as for this one, multiplicity of 3, that's going to be a point of inflection because it kind of changes its concavity a bit. It's kind of got like a bit of a swerve to it. That's what we just call a point of inflection. All right, moving on. Question C. The degree of p of x equals blank, and the sum of multiplicities equals blank. Well, the degree of the polynomial, you can tell just by looking at the equation here, the degree of the polynomial is 5. And what do you know? With the sum of multiplicities, 2 plus 3, well, that is also going to be 5. You sure hope it would, because the degree and the sum of multiplicities need to be the same. Last question here, write the polynomial in fully factored form. So in other words, write it as p of x equals a, that's a leading coefficient, times x minus b squared times x minus 3 cubed. So there's our multiplicity of 3 and our multiplicity of 2. Well, because we had an x-intercept of -3 and +2, these are what's going to make your binomial equal to 0. So if we had some binomial equal to 0 when x is -3, well, that would mean we'd have to have a +3 attached to it as well. So in other words, for this first one, we have x plus 3. And for the second one here, we would have to have x minus 2, because if x was equal to 2, 2 minus 2 is 0, and that, of course, gives us our x-intercept. So long story short, my multiplicity of 3, was it? No, my multiplicity of 2 is going to be x plus 3. So I know I have p of x equals, give myself a little space for that a value here, x plus 3 squared and x minus 2 cubed, because that one was a multiplicity of 2 and this one was a multiplicity of 3. Now your a value, this number out in front, your leading coefficient, it's actually the same as the leading coefficient in unfactored form. That's what's really brilliant about this. Leading coefficients, the number in front of your highest degree term, that doesn't change, even in factored form. When it's all said and done, you'll still have it sitting on the outside. Our leading coefficient in this one looks like it was a -1. So I'll just tack a negative on the outside there. If you feel more comfortable, you can put -1. It's up to you, whatever floats your boat. Either way, though, look at that. Just by using our graph that we drew, this really crude graph that I did here, just by using this graph, I was able to write the factored equation for this. The only thing that I kind of needed was that leading coefficient from before. We'll get into that next day on how we can calculate that without it, but don't worry about that for now. All right, so this next one, I don't want you to use a graphing calculator for this one, but the good news is I factored it for you. So I want you to consider the polynomial function p of x equals x to the power 6, blah, 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 blah. What you're really going to care about, let me be real here, what you're really going to care about is the fact that I've got this in factored form for you. You're welcome. We weren't going to go like deal with this -24 here and then use the integral zero theorem and all that to go nuts on this one, right? No, we're not doing that. We're just going to use this factored form right here. So complete the table. And once again, for description, state whether it passes straight through and blah, 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 right? So given this table here, we do clearly have 3 zeros. The first 0 is this one. That's going to be x is equal to -3. That one looks like it has a multiplicity of 1 because there's no exponent on it. So for a description, if something has a multiplicity of 1, then that means theoretically it should be passing straight through the x-axis, right? It shouldn't be doing a little divot. It should definitely not be tangent. It should be going straight through the x-axis. The next 0 that we're going to have is x is equal to -1. That's what this one would be right here in the middle. And that one has a multiplicity of 2 because of the exponent 2 on it. And if something has a multiplicity of 2, that's going to form like a little quadratic at the x-axis. So that's going to be a tangent. As for the last one, we have x is equal to +2. That would be our last 0 here, and that one has a multiplicity of 3. And if something has a multiplicity of 3 or any other odd number bigger than 2, it's going to be a point of inflection. So you might see where we're going with this. We've broken down what these zeros are, what their multiplicities are, as well as what a description is for what each of these zeros look like. So let's first talk about the degree of p of x and the sum of its multiplicities. Well, again, you can tell the degree of p of x simply by looking at its unfactored form. It has a degree of 6. And the sum of multiplicities, well, 1 plus 2 plus 3, that is also 6. Those two numbers always have to be same. Now, without using your graphing calculator, roughly sketch the graph of this polynomial on the provided grid. You'll want to set your quote-unquote window. So we'll want to draw our window using this window setting right here. This is a very similar window setting that we had, or from what we had before, except this time y is the same going down as it is going up. Our y min is equal away from 0 as our y max. So this time around, if I'm going to draw my grid, give me a second. If I'm going to draw my grid, it's going to be pretty symmetrical. So I'll kind of pick the middle of this as best as I can to draw my y-axis. There we go. And then I'll also pick roughly the middle of this to draw my x-axis. I'll do that about right there. Hopefully that is going to be good enough. Now, in terms of my scale in the x direction, -5 to +5 with a scale of 1. So I can say scale of 1 here is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Perfect. It works. So let me make sure I fill that in so I don't forget. 5, and then -1, -2, -3, -4, -5. Honestly, this is just a skill that gets built over time. So if you're uncomfortable with this, I understand, but it is what it is. Anyway, in our y direction, our scale this time is 20. I think I can safely make it every 2 here. So 20, 40, 60, 80, 100. Oh yeah, that was no problem. And then this is -20, 40, 60, 80, 100. So let me just label all that. 20, 40, 60, 80, 100, -20, -40, 60, 80, -100. I bet that was super thrilling watching me do that. All right, so if we're going to do a rough sketch of this, this is where I'd really like to go back and look at that table I did. Notice we had 3 different zeros with different multiplicities. We had -3, -1, and 2. So at -3, -1, and 2, I'm going to put some dots here. Just let me know that I'm going to have some zeros there. Now, the intercept here at -3, that's going to have a multiplicity of 1, which means it's going to go straight through. The next one will have a multiplicity of 2, which means it'll be a tangent. And then the last one will have a multiplicity of 3, which is like a point of inflection. Now, the tricky part of this is, though, it's all well and good to say, where am I? There we are. It's all well and good to say that we're going straight through at -3, but are we going straight through this way? Or are we going straight through this way? That's a little bit tougher. In order to determine that, it would probably be a really good idea to look at your leading coefficient here. The leading coefficient in front of this polynomial is +1. That means I know, remember from earlier, I know I'm going to be ending up here in quadrant number 1. So maybe, because I know that, maybe I should start going from right to left here. So I'm actually going to start by looking at my x-intercept of x is equal to 2. X is equal to 2 as a multiplicity of 3, which means it's going to be a point of inflection. That's one of those curvy things here. So I know there's going to be a bit of a curvy thing here, but I also know I need to end up here in quadrant 1. So that tells me I'm going to have something that looks something like that. Now, I have no idea where it goes from here. It might even do a bit of a curve. I have no clue, and that's okay. We're just doing a rough sketch of this. We're not using our graphing calculator. There's no confirmation there whatsoever. Now, the next thing we need to do is, of course, deal with our other zeros here. At -1, we have a multiplicity of 2, which is a tangent. Because we're down below our x-axis here, the tangent is also going to have to be below this because there's no way we're going to be able to cross the x-axis from here to there. So I know we're going to look something like this right there. So I'll just draw it like that. The last one we saw, -3, was the first one on our chart. It has a multiplicity of 1. So that means it's going straight through. There's only one way we can do that, and that's just by going straight through and then going up this way. Now, the tricky part is I have no clue how far down any of these things go. Like connecting this point to this point, it's just basically a guessing game at this point because we don't have enough information. I could plug in a bunch of numbers and play around with it, but nobody's got time for that. I'm not going to do that, right? So long story short, what I will do is I'll just kind of like draw a little bit of a divot here. One thing I can say is I know it's going to pass through -24 because that's our y-intercept there, but whatever, if you missed that, that's not the end of the world. And then as for here, I'm just going to like pretend it's going to do something like this, and I just need to know it's going straight through that way. So that'll probably be good enough. It's entirely possible that maybe over here it dips way down below here, or over here maybe it kind of like does a weird like little divot-y thing. I have no clue, right? We're not going to be going that deep into this right now. You'd be using your graphing calculator to confirm those sort of things. We just want to get the general shape for this. Now, what I'm hoping you notice is both of the ends of this function are ending above the x-axis. That tells me that this is an even polynomial, and we sure hope it is because we can see the degree of this polynomial was 6, so it should have been an even-shaped polynomial. Wow, that was it. So told you it was a bit of a longer lesson, not terribly bad, about half an hour long. For practice, make sure you're trying page 147, questions 1 to 9. And then, of course, we want to get close to wrapping up our Chapter 3 assignment. Just a bit of a disclaimer, though, you might want to leave question 15 and the diploma question for next class, because those questions will be more aptly suited to then. Everything else, though, you should be able to get done at this point. I cannot stress enough the importance of doing those textbook questions as well. I know they're not for marks, but it is a good idea to get some additional practice at this just to be sure. As always, if you have any questions, please let me know.